Suppose Amazon wants to group customers based on their purchase history, so when Amazon recommends products, the customer has a higher chance of purchasing. To do this, Amazon will attempt to take a customer's purchase history and compare it to other customers with similar purchases. This is an example of where a DBSCAN algorithm would be useful. DBSCAN, otherwise expanded as density-based spatial clustering of applications with noise, is a data clustering algorithm meant to solve the general problem of how are these data points related. To do this, the algorithm employs a nearest neighbor-esque line of thinking. It classifies each point as either a border point, a core point, or a noise by determining the number of points within a spherical radius of it. The number of points within a spherical radius is a tunable parameter which determines the classification of the points. For example, if the number of points required is 5, then a core point is a point with 5 other points within its spherical radius. A border point is a point that does not have the required number of points to become a core point, but one of the points in its sphere is a core point. A noise point is one that fails both the number benchmark and the core point check. The clustering groups the core points to other core and border points until distinct clusters are created and no core points remain. Using the example above, we can take a customer and group them based on their purchase compared to other customers. If they bought a cat toy and a cat bed, and other customers purchased a cat toy, cat bed, and cat litter, then the algorithm will group them together for the same recommendations of cat food. This algorithm has a heavy background in machine learning, a topic some people might not explore while they earn their computer science degree or in a career in general. There are some examples, but a lot of them aren't clearly explained or aren't very transparent at every step. Thus, for the +1 element of our project, we are presenting a clearer explanation of how DBSCAN works using a graphical visualization and comparing that graph to the results of another clustering algorithm known as k-means clustering. We are using the P5 Python package to plot points in an animation-like style to show how different parameters of DBSCAN affect the resulting clusters. When we ran k-means, we used the same number of clusters that DBSCAN found. For simplicity of visualization, we used a 2-feature dataset to plot the data points in a 2-dimensional space.
With k-means clustering, we start off with randomly creating central points called centroids. We then assign all of the data points to a centroid based on which centroid is closest to the point. When all of the points have been assigned, then the centroids will be moved to the mean of all the points in its cluster. The process is then repeated until the total change for all of the centroids reaches a threshold value. One of the main weaknesses of the k-means algorithm is the fact that it requires a convex dataset to provide accurate predictions. In this case, since the data is not in a convex shape, the k-means algorithm will incorrectly predict the clusters. It is also sensitive to noise and will take into account all of the noise values for determining its means. With DBSCAN, the limitations of k-means clustering are resolved. When it classifies each point as a core point, border point, or noise point, it will randomly select a core point and create a cluster from the nearby core points until it cannot find any more. If there are still more core points, then it will start a new cluster originating from the next randomly selected core point. This will repeat until there are no core points remaining. The main limitation with DBSCAN is the impact that the multiple input parameters can have on the algorithm. Changing the number of minimum points can either increase or decrease the number of clusters depending on the density of the dataset points. Changing the distance measurements or the size of the circle around each point can also impact the number of clusters that will be returned. Because of this, using DBSCAN requires a fairly strong knowledge of the layout of the data and extra time for experimentation with the data. As you can see, changing the EPS and minimum points value can dramatically change the predictions of the DBSCAN algorithm. Just by changing our EPS and min value from 1 and 1 to 5 and 4, we can see that it will return some clusters, 3 to be precise, but each cluster only had 1 to 4 points in them, whereas changing it to 15 and 4 will create about 10 clusters, each with varying amount of points in them. This occurs because of the different densities being calculated and the input parameters not being correctly decided. When we change our input parameters to 20 and 4, it starts to appear that we have found that sweet spot with our input parameters where it accurately predicts the clusters and throws out all of the noise points, as you can see right now. Changing the EPS to 50 and the minimum points to 4, we see that we have overdone it and we have assigned everything to one cluster. For both of these algorithms, they have their advantages and disadvantages. For k-means, you will have to guess how many clusters there will be, as well as assume your clusters are all convex. But k-means requires very little input parameters. DBSCAN, on the other hand, requires a lot of input parameters that have to be adapted for each data set through experimentation. It benefits, though, from the flexibility of being able to cluster non-convex data as well as convex data with a high precision.